Alright, sorry about that. Just trying to get the microphone sorted out, but I think it's still not working. People have been asking about the field trip. We still haven't split you into the two groups yet because there's still some people that haven't registered on the course yet. There's just a few people aren't registered, so I'm not going to split the groups up. But by tomorrow, I'll have sorted out which group's going on the 17th and which group's going on the 23rd. Okay, it doesn't make any difference, but I can't do it until I know everyone's registered. If you haven't got your waterproof clothes yet, Aldi on Thursday start to sell their winter waterproof clothes. So if you want to go to Aldi, it's Bike Week at Aldi. So they've got waterproof clothes for riding a bicycle, and they're very good. And they're only £15 for a top and a bottom. Anyway, that's more. Okay, so from last time, I asked you to read through the proposals that I put on Blackboard. You made some marks for those. I checked, there's still quite a few people who haven't done that yet. So if you haven't done it yet, will you see if you can spend a bit more time and get those done? So then we can go through the actual marked ones to give you an idea about those. Maybe if you haven't done it, just have a quick go at doing it, and we'll just try and cover that tomorrow. We'd like to get that out of the way now, so we want to move on from that. So just check. If you haven't done it, just have a quick go through, and then tomorrow we'll spend a little bit of time just going over those proposals, so I can show you what the markers thought of them as well. Okay. And there's no point doing it now because there's still quite a few people that haven't actually done that. Okay. We'll also go through working out the average of that. If you remember, we put this little program up. So instead of doing that today, we'll do that tomorrow because there's still quite a few people that haven't actually put their marks into the grid. And then we'll also show you the program. Just spend a little bit of time just going through the steps in that program, which there's a video on anyway, so you'll see. We won't spend a long time doing it, but instead of doing it now, we'll do that tomorrow. The other thing I asked you to do was to at least have a look through this section. Actually, I might as well start on this. So you also look through the first couple of sections here. To be fairly blunt about this, right? This is a very basic level of statistics, right, that you will have done before. So my role really is to tell you again in such a way that you see how important and useful it is so that you do use it in your projects. We just had the exam board for last year's students. So we've been looking through all projects. And the same sort of things happen again. Many of them have used basic statistics and much more, but there's still some that aren't using the most basic statistics. So in some ways, I don't want to use the word remedial, but it's kind of remedial really. You do know this, but I just want to reinforce it that this is what you should be doing. So this first few sections that we're looking at in this block are really leading towards how you compare one thing with another. You know, we talked about kinds of research projects, and we said that there's a limited number of types of research projects, we were saying last week, and one of the simplest would be a project that just says, is this thing different to this thing? And an example for you guys that fits with pollution would be a question, is this site more polluted than this site? Or is this site polluted? And you just make a comparison of one thing to another. Or if you're more biological, has more copper accumulated in this muscle than in this muscle? Right? There's lots of projects that are like that. And it's just about saying whether one thing is different to another. If you think, well, that doesn't sound very involving as a project, it is involving because you have to show that it's really true, that it's not a matter of speculation. If you want to demonstrate there really is a difference between this one and that one. And I said last week, the big problem often is that you don't know what the concentration of a contaminant was to start with. So if we had a problem which is this site contaminated? You think it's straightforward to answer, but the question is, well, what are we measuring it against? Is it contaminated compared to what? That relies on there being some measurements in the first place. And I said to you last week, a huge problem that you'll come across in the work that you'd like to end up doing is there's no baseline data. That's the term you'd be expecting, baseline data. And there's often no baseline data because no one was bothered about whether there was pollution to start with. So there's no idea of whether it's polluted to start with, so quite often you're trying to see whether it's different to baseline. We're going to go through an example of how we deal with that as well when we get a bit further into this. But I want to try and pick up the themes really that are here. So we're going to talk about the different sorts of projects. But straight off then, for these few sections we're going to look through that you've looked through already, what we're working towards is the basic statistic that will allow you to say one thing is different to another. Okay. So if you've worked through, I've seen many people have worked through this because it shows on Blackboard if people have done these little tests. It's not really a test, as you know, it's a dialogue. Okay. In the Western tradition, this would be what's called a Socratic dialogue. It's a dialogue between a teacher and a student. So we have a conversation and tell you the answer and we work something from there. Okay? How exciting is that? It's not just something I casually wrote, this is Socratic dialogue. Make sure you put that on your CVs that you've been involved in that at Manchester University. So, having done that, I'm going to ask you, well, actually, to see. Right. This is how we go about quantifying variability. But from the first part then, if you looked at this, and it's all something that's quite well established, you've done before, why do we make multiple measurements? That's what's going to come out of this. If we're trying to find out whether something's different to something else, we make multiple measurements. Can anybody, and I know a couple of people I'm looking at right now, you try not to look at me. People that I've seen before. Why do we make multiple measurements? What's the reason we make multiple measurements?
To find the true value, financial value.
How does making multiple measurements? Well, you said we make multiple measurements to find the true value. Is there any comment to make on that? Comment would be: do you agree or you disagree? And then, if you agree, then how does it help by making multiple measurements? Just to get everyone involved. Thanks for joining in. Everyone can join in now. Oh, go on.
Maybe to maybe cancel out any sort of contamination from one sample.
Okay. Somehow reducing the error. Let's make it more general. I know I've said our final example is going to be how can we tell if one site is more contaminated than the other. But as a more general thing, why do we have multiple measurements? It matters a lot to you guys because many of you will be doing projects that involve making your own measurements, and your projects would take 33% of the time they're going to take if you didn't make triplicate measurements. Mostly we'll make measurements in triplicate or multiple times. If you didn't, then actually you could fit in, during your summer break, you could fit in quite a long holiday if you didn't make multiple measurements. Okay, so we should really be clear why we do make multiple measurements. So we've come up because it gets us closer to the true value. Does anyone got any further gap?
It can reduce human error. The idea is that it reduces human error. Increasing the likelihood that you are measuring the correct measurement.
Yeah, okay. That I think both of you are working towards one of the answers as to why we make multiple measurements. And I'm grateful, sincerely grateful for your input. It's nice to, it's hard to get input from lots of people, so thank you for that. So don't be off-put now by me saying the point you've come up with is the easier one of the 2 points that we're going to make. So I'm probably, if you look through this, then you'll have seen this argument anyway, but it's an argument that's well worth rehearsing, if only because you know there's a short answer multiple choice test at the end of this. But the starting point for us must be that a measurement that we make can never be the true measurement, except in which case you can jump in. Like if you look at this dialogue, you'll know the answer to this. But I'm saying you can't make a true measurement. Generally for the measurements we make, you can't make a true measurement, except in which case. What things can we make a true measurement of? What kinds of variables can we make a true measurement of? Yes?
Discrete variables?
Yeah, discrete variables. Okay, so in the example in this, if we were counting limpets on a shore, which some of you will do because you're interested in contamination in limpets. Others you're thinking that's very, very dull, but I'm kind of interested in contamination in limpets. It's a good thing to do. But you could count the number of limpets. You can count them as discrete variables. I could say there are 10 limpets. Because they're discrete, I can say there are 10. Most of the other measurements we make are continuous variables. And as far as continuous variables are concerned, our view, well, not our view, the reality is we can't make a true measurement of a continuous variable. So what you have to recognise is that if you make a measurement of a continuous variable, it's one of a family of measurements. It's one of any set of measurements. You can measure it again and you'll get a slightly different result. If you go to so many decimal places, you get a different result. And when I say it's one of a family of measurements, how big is the family? How many measurements could we make? Again, there's a theme to this, like most of the questions I'm going to ask you will have exactly the same answer. By the end of the course with me, I hope everyone will be joining in with the answer, because it's always the same answer, pretty much. How big is the family of measurements that we could make? Go on, say it loud. It's infinite, okay? So there's this theoretical infinite family of measurements we could make. So we could make our measurements of a continuous variable an infinite amount of times. If we made it an infinite amount of times, then, as our two brave speakers have pointed out, then actually we could get the true value. The definition of the true value of a measurement of a continuous variable would be the average of an infinite number of those measurements. So we can sort of breathe a sigh of relief now, because we started off by saying we can't make a true measurement, at which point we're kind of thinking, well, we might as well go home. But actually we can make a true measurement if we make an infinite number of measurements. So we still think we might have to go home because we can't make an infinite number of measurements. So that's the first part of the argument, the second problem. If I go back to the question, let's see if we can address the question then. So why do we make multiple measurements? Now we've dealt with what you two guys have said. Like making multiple measurements is closer to making an infinite number of measurements. Okay, so it's going to be better because you're making more of the family of measurements. So you will be closer. So multiple measurements does get you close to the true value. So that's some value to it. So you could put a tick and say, I'll explain why we make multiple measurements. It's better to make multiple measurements than just making one, because it gets us closer to the true value. But, like, this is really a central point that we're going to come back to over the rest of this and over really the whole of your career. So you'll remember this lecture. Not just because the microphone didn't work, but you'll remember this lecture, right? That it's not enough, really, is it, to say we've made a measurement. Because we made multiple measurements, it's closer to the true measurement. how much more valuable is the fact that you're closer to the true measurement than if you just made a single measurement? It's a bit more valuable, but actually for that measurement to be valuable, the missing bit of information really is how close to the true measurement are you? That's really that's the smart bit, that's the clever bit. It's not really that clever to come up with, well, if we make some more measurements, then we'll be closer. It doesn't really help you to say we are closer. Being closer doesn't help you. You need to know how close. The definition is you can't have the true value. If someone tells you, this is my answer, it's closer than if I'd made a single measurement, but that doesn't really help you very much. What would help you a lot would be to say, here's my measurement, and this is the likelihood that how close it is to the true measurement. And working that likelihood out is really the smart part. And here we're talking about a very basic statistic, but actually, as a general point, the same thing applies. Most of the work that you're going to be doing will often be, it's quite easy to come up with an answer of some sort, but the work goes into saying how good is that answer? How reliable is the answer? And that's typically the sort of work that we have to do. And your clever thinking bit goes into the how reliable is the answer. So having said all that then, let's come back to the question. So why do we have multiple measurements? Well, number one is that it comes to our mind first, but probably not the most important reason, is that by making multiple measurements, we do end up having a value that's closer to the true measurement. But what else does making multiple measurements allow us to do, given what I said, is the clever thing? Let me rephrase the question. Right? I've said to you that coming up with the measurement, not that difficult. Doing it multiple times, a bit more difficult, and therefore coming up with a measurement that is closer to the true value. But actually, if I just say to you, I've got a measurement and it's closer to the true value than if I'd done it another way, that's not that useful. But if I could say to you, I've come up with a measurement and I'm 95% confident that it is the true measurement. Now that actually starts to be something that you can go to the bank with. That's something you can use. So that's what we'd like to achieve. How does making multiple measurements allow us to achieve that? Yeah.
You can run statistical tests on it and test for significance.
That's not wrong. Okay. I guess it's really difficult because I'm here at the front and I've read all this and you're just having to answer. I know what you're trying to say. What I'm really trying to dig into is I want people to say precisely what's going on, and I think what you're trying to say precisely is that it's by making multiple measurements, it means that we can actually quantify the variability. Right? But these are when I say rehearse an argument, you need to use these words. There's not really another way of writing this argument. You know, when you make multiple measurements, it means that we can quantify the variability. If we can quantify the variability, then it means that we can actually then give a probability of how close our answer is to the true answer. Okay, and that's why we make multiple measurements. Right? And this could seem dull to you because you've done this over and over, but I just want to make it really clear. And the best way of doing that is just let's just go through the argument again, and then we'll understand why we make multiple measurements. So the starting point in our argument is that as far as continuous variables are concerned, we can't make a true measurement. At which point, we're very sad. Okay? So just follow the arc of the story. We're very sad. We can't make a true measurement. However, the reason we can't make a true measurement is because we recognise that the measurement of continuous variable is one of a family of measurements. That gives us a little bit of hope. We know the size of the family. The size of the family is infinite, but if you could make an infinite number of measurements and take the mean of those, then that would be the true measurement. So we're trying to get that true measurement. So we got a little bit happier, and then when we realised that we need to make an infinite number of measurements, we're quite sad again. Okay. But it does point out to us, though, that if we make multiple measurements, we make more than one measurement, we're going to get closer to the actual true measurement. Once we recognise that the true measurement needs to be the mean of an infinite number of measurements, we know that if we make more than one measurement, then we'll be getting close to the true measurement. So we're a bit happier. But it's not the best we can do, right? And I think now we're jumping into what we should be thinking of as scientists. It's quite obvious, really, that if we make more measurements, we'll get closer to the true measurement. But it's recognising that just saying that we're closer isn't really very useful. You can't do anything with that. It's a qualitative thing. Just saying, I know we're closer. What we do need to do is to say how close. Once you say how close, then the measurement's valuable. Like, you wouldn't want to use that measurement on the basis that someone said to you, it's closer than if I hadn't made multiple measurements. That's no use to you. But if you can say, we're 95% confident that it's this measurement, then actually you can work with that, you can do something with it. Okay, so that's what we're trying to achieve. And in order for us to be able to do that, we do it on the basis of the variability of the measurement. So, see, if the measurement's very variable, then we're going to be less confident in the measurement we come up with. And how do we know if the measurement's variable? The only way to judge whether a measurement's variable is to make it more than once. So that's why we make multiple measurements. So there's two reasons then. One is by making multiple measurements, it definitely means that we've got a better estimate of the true value. But more important than that is, by making multiple measurements, we can quantify how good our measurement is. Okay. Is everyone on board with our argument? Okay. I realise that this is stuff that you know, but you need to think about it in that way, and it will matter as well. We're going to use the same argument when it comes to this. We're talking about this making a true measurement. There's lots of other ways of making, well, more complicated ways of making true measurements. We're going to use a model to work out what's going on in a particular situation, and we adopt the same procedure with that. We need to know how good our answer is, like whether it's from a basic statistic or whether it's from a complicated model. The next thing still is like, how good is the answer? And the hard bit often is saying how good the answer is. It's easy enough to come up with some sort of answer. The problem is to say how good the answer is. And that's where our work's going to lie. Can I just check, right? How many people did look through this stuff? You did. So it's just my hammers to bore you with it, really. So tell you what, it's this. You'll have done this anyway, but this just illustrates what I was saying. I mean, that's why if you've done it, you're probably slightly bored by what I've just been telling you. But we're talking about variability. The first way then of looking at the variability is you could plot the data up. And we've got two graphs here. The data set that I've given you is it's an old data set now. I remember when it wasn't old, but it's an old data set of student heights. Here we've got a more dispersed distribution, here we've got a narrower distribution. And the question that was being posed here, actually we might as well, you've done this, we can all join in with a show of hands and answer the questions. So the average height of a University of Manchester student using 500 students entering this building in 1999-2000 is shown as these frequency distributions, in which year is the sample mean more likely to be equal to the population mean. So on the left-hand side, for you, we've got a wide distribution. On the right-hand side, we've got a narrow distribution. This is 1999, this is 2000. So put your hand up then if you think that the sample mean is more likely to equal the population mean in 1999, the left-hand side. Remember, you have to put your hand up for one of them. Right. Who thinks it's more likely to equal the population mean in 2000? Oh, this is the best ever. Everyone joining in? Okay, so we're all right with that. All right, the rest of this then, again, seems like you've been through this, but the point of it, which I hope you got anyway, was if we've recognised that we need to quantify variability, that's the critical thing in making our measurements, we need to quantify variability. The next question that any sensible person would ask is, well, how do we quantify variability? And I know that this is like you seeing the film that you know the end to already, because you've read the book or something like that. But I know the end of this is something that you know, because the end of this is standard deviation. That's where we're going, so no point hiding it. And you're used to the standard deviation. But I wanted to get you to invent standard deviation yourselves. That's really what's going on here. So the idea then is we need to measure variability. And by doing this, it just makes it clear in your mind what you're doing when you're using a standard deviation. Because now it's very easy, you press the button at the standard deviation. But really, it is a measure of variability, and it's one that you would come up with yourselves, I think, up to a point. So if you wanted to measure the variability, there's a couple of ways of doing it that are no good. So if you wanted to you could look at the range of the measurements. The range of the measurements is not a good measure of variability because, why not? I mean, the range is a measure of the variability, isn't it? But why is it not a good measure of the variability? Philip? Like you all know, come on, help me out here. Yeah, it only uses 2 points, so that's why it's not very good. So we only use a measure of variability that uses all of the data, and it doesn't take too much thinking to think, well, if we have a cloud of data and you've got the mean value somewhere here, then the measure of variability is how different each data point is to the mean. So we could measure the difference between the mean and each of the data points and add them all together, and that would give you an idea of the variability. That's what you would come up with if you were tasked with a measure of variability. The first problem you would run into is, of course, that if you sum together all the differences between the data points and the mean, they'll all sum to 0, and your measure of variability would always be 0. So you need to disregard the sign. And that's what you have to do in this. Looking at this data set, you disregard the sign, you come up with a number. If the number's very big, does that mean you've got a variable sample? The bigger the number, is it a more variable sample or a less variable sample? Again, a very stupid, simple question, but just to get us all involved, get warmed up. What's the answer? Big number, is that more variable, less variable? Who thinks it's more variable? Put your hands up. All the way up to it, come on. Help me out. Please, right. Yes, thank you. It is more variable. The bigger the number means it's more variable, isn't it? If it's a small number, it's not very variable. I'm assuming that you're just humouring me and that you're all right with this. All right. So far then, we've come up with a measure of variability, which is the difference between each data point and the mean, all added together, but disregarding the sign. So whether it's plus or minus, we disregard it, we're all plus. So we made it plus or minus, it would sum to 0. that's a pretty good measure of variability. The only thing that's missing is that if we've got a large sample with lots of data points in, then we're going to get a larger number. And because that number's larger, it doesn't necessarily mean it's more variable. It could just be to do with the size of the sample. So how do we deal with that? Okay. We standardise it, don't we? We standardise it by dividing by the size of the sample. So that's the measure. You should be patting yourselves on the back now. You come up with a measure of variability that you understand, right? We started off with saying we need to have a measure of variability. This is the measure we've come up with. Difference between the mean and every data point, added together, disregarding the sign, divide by the number in the sample, so that's standardised, so regardless of sample size, it's a statistic that's going to work. And that's clearly a statistic that gives you the variability. So we could use that in some way. If you've got two data sets, and you wanted to say in which one of these is the mean more likely to be close to the true mean, you would be able to say using your statistic. So we're doing some of the things that we said we needed to do, which if you scroll all the way back up at this point we're just trying to make measurement meaningful. From our starting premise that actually measurement isn't meaningful because we can't make a true measurement, we're working our way through to making measurement meaningful. So we're pretty pleased, I think. Pleased with the results. Yes? Okay, so we have that statistic. And then this, I know that you sort of know this, but when to put this together as the argument, we've come up with a statistic that we understand. I appreciate that some of you have a very deep understanding of statistics and standard deviation, so what I'm about to say may not apply to you, but this is the clever bit really now. The measure of variability we've come up with at this point, we understand it. If you were to compare the measurement that you've come up with, that if you understand much more than this, then just bear with me. But let's say this is the measurement that you understand. We've been through it, and we understand how we've derived this measure of variability. The mean, all the points away from it, added together, divided by the number in the sample. We understand that. If you compare that, the formula for your statistic, to the formula for the standard deviation, you'll see they're not quite the same. Okay, what is the difference? Anyone? Okay, I'll tell you the difference. In your formula, you've looked at the difference between the mean and every data point, and you've disregarded the sign. So in Excel terms, the formula you've used is ABS for absolute, so you're taking the absolute value of the difference. In the formula for the standard deviation, you've got the difference between the mean and each of the data points, and you've squared it. Okay, you haven't made it an absolute value, you've squared it. Now you can see that squaring it is the same thing as taking the absolute value. If you square it, it's always going to end up as a positive number. And it's possible that when that's been explained to you, maybe at school, about doing the standard deviation, that would be the reason why you've taken the square, because it means that you get a positive value. And as we said, if you don't do that, if you don't make all those differences come out as positive, then your measured variability will always sum to zero. Okay? So in standard deviation, though, you're squaring it rather than taking the absolute value. So the question really is, well, why is that then? Why are we squaring it? I understand why we take the absolute value, but actually in the standard deviation, we're squaring it. And the reason for that, again, you will have looked through, but we can mention it. The critical part, again, of the argument really is that in our attempts to come up with a measure of variability, what we've done so far in our attempt to determine whether the sample mean is likely to be close to the true mean, we've not made use of any assumptions about the distribution of the measurement in the whole population. The only assumption we have made is that the latter is similar to the sample distribution. So far we've just been working without making any assumptions about the way that the variability is distributed. We just assume there is variability. We're not making any assumptions about how it's distributed. And that seems quite a reasonable thing to do, because the variability we're looking at is the variability that's coming from differences between making one measurement and making it again. So differences that are due to random factors. So why would we assume there's any kind of predictability in the distribution of variability? So we haven't made any assumption about that. But actually we can make an assumption about the way that the variability is distributed. Okay. Again, this will likely seem familiar to you. If the variation of the measurement is a result of random, indeterminate processes, it's possible to make some assumptions about the distribution. And if you've done this, you can look at this. I'll show you this because we're going to use a similar sort of approach in Excel as we go further into this. So probably next week, when we're working towards, again, just to recap. I guess at the moment we're looking at how we tell the difference between two things. And ultimately we're going to look at using models to say whether a certain situation is different to another. So we're building up the complexity of the analysis really that we're doing. And when we're going to be using some models, they're going to be very similar to this. So there's two reasons for looking at this. This is a simulation for you to see random processes working, but the way that it's actually using Excel is a way that you can use Excel for a modeling process. In the end, that's what's going on here really. It is a model. So the premise for this is that we've got lined up on a line. You should be pleased that we're doing this, right? However dull it might seem, it could be much, much worse, because you could be all having coins to toss, right? And Neil Mitchell, who'll be teaching you after me, did used to have you tossing coins. He's not doing it anymore, he's told me, so you don't have to do that. But what we have then, in this bottom graph, is 500 things that can move either left or right. If you imagine a coin, it could be either heads or tails. They can move left or right. Each time, every time step, the things can move left or right. And we want to model what's going to happen if we have 500 things that can move left or right, and see how far they move away from the centre line. So, on average, how far is something going to move from the centre line if it can move 50% of the time it can move left and 50% of the time it can move right? Where would you expect most of these things to end up? They start at the centre, they can move 50% of the time to the left, 50% of the time to the right. We let them move over and over again. Where are they most likely to end up? Yeah, where they started, okay? Because they can move left just as likely as move right. So most likely they're going to end up where they started. All right. So if we actually let this run. Okay, so you've got to see this little counter this is the joy of a computer, right? Instead of you tossing the coins, the computer is tossing the coins. So this is saying, we've let this run 100 times now. So after 100 times, they're not all on the centre line. Again, no surprise to you. They are starting to, the words, they start to disperse, okay? And talking more about this. And then up here is a plot of this. This is in the light blue colour, it's a plot of the position of each of these. So how many of them there are at this distance away from the centre line. And in the dark colour, that dark colour is produced by a mathematical equation, okay? And that's actually the Gaussian equation, okay? So it's a Gaussian equation. So we're comparing the real world, although it's inside a computer. This is the real world is compared to the Gaussian equation. If we let it run on some more, you see the distribution starts to flatten out, but also the correlation between the actual distribution in the real world and the Gaussian equation just get better over time. The more times you let this thing run, the closer it gets. So you see two things. One, we've got dispersion going on, and two, it starts to match up more and more with the Gaussian distribution. So the point I'm making here then is that we can make some assumptions actually about the distribution of the variability, and it's to pull it together, your measure of variability, which you understood, pulling that together with actually having some idea about what the distribution of the variability is, that allows us to come up with the standard deviation. That's where the standard deviation comes from. So the equation, the Excel version of the equation for the Gaussian distribution is written in there. Right, as far as your test's concerned, you're never going to have to write out the Gaussian equation, but you'll recognise it. It involves pi, it involves an exponential function, but critically in there is the standard deviation. The formula for the standard deviation plugs into the Gaussian distribution, so there's a connection there to the Gaussian distribution. There's two variables in the Gaussian distribution. So the distribution that plots the variability that you actually get from pure random variability, there's the mean is in there, which tells you where the centre line is, and there's a term that tells you what the spread of the distribution is. Let's get back to that. So the spread of that distribution, in order for you to fully specify the shape of that curve, there's two parameters you need. One is the mean, which tells you where the middle is, and the second is the parameter that tells you what the spread of it is. Okay, with those two things, then you make a specific Gaussian distribution. The Gaussian distribution on its own is an infinite number of different shaped curves. They're all this bell shape, but there could be any kind of bell shape. For a specific one, you need the mean and the measure of spread. The formula for the measure of spread is the formula for the standard deviation. And you can kind of get it because you know that your formula for variability is very close to the standard deviation. Your formula was the absolute value of the difference between the mean divided by the number in the sample. The standard deviation is when you squared it. And that's where the standard deviation comes from. It relates directly to the normal distribution. And so we're linking together some understanding of the distribution of the variability as well as just our fundamental idea about what the variability might be. And that's why we end up using the standard deviation. And what that allows us to do is to start giving percentages of probability that our measured mean is likely to be the true mean. And that's ultimately what we're going to get. We want to be able to say quantitatively how likely it is that our measurement of the mean is equivalent to the true mean. And because of this coincidence of the standard deviation with the Gaussian distribution, it allows us to say that. And if you, the best way to do this, if you haven't done it, is to work through these examples. What happens next is that you actually come up with your own statistical table, which, when I was at school, we actually had statistical tables that you'd have to pay £1 for, where they'd have all of the numbers written in them. Nowadays, you don't see that, because you just press a button on a computer. But actually, it's good for you to just work through, and you can actually come up with your own statistical table, which will let me show you how this works. Download the... Right, it's 9:50, which means that you all deserve to have a break now, so you can wake up. If we start again at 10 o'clock, then we'll just finish this off. I'll just show you how you do your statistical table. Again, I realise many of you have been through this, but let me just quickly show you that, and then we can move on from this. But you need to, I don't know, get some fresh air or whatever after 50 minutes. So if you do that. Hiya.
Hi. I'm in your group for the tutorial.
Yeah.
Are we meeting today after class?
If you can, because
Yeah.
some of it could only be today. I didn't send the confirmation email. It's just that everyone seems to be available.
Yeah.
Is that okay?
So directly after class, or
Well, you can decide later.
Okay.
Probably don't want to be very long class, but I don't know how long.
yeah, I mean, I'm pretty like I don't have any other class today, so
Well, I'm fine. Maybe it's like above 31. The guys that do my tutorial. Wow.
In these topics, we can see about that's a test.
Yeah.
And also,
can't see this?
Yeah, and on our computer or on our phone.
You can't see the video?
No. It's just a picture. There is a thing.
Oh, this picture? I don't know why. It doesn't matter really. Okay, because mostly it's
Okay, but this time,
Yeah.
you can't see.
You can't see those pictures.
So we can't do this.
Okay. I'll see what I can do. Yeah, but don't worry. It's not assessed. So.
I want to ask, are you putting lecture recordings into the Blackboard?
Yeah, actually, I am. So that's recorded. Okay, let's carry on. Okay, so just to recap, we started off thinking that we couldn't make any meaningful measurements, and now we've worked through to actually recognising we can make measurements meaningful by saying how good they are. And in order to do that, we need to measure the variability and quantify the variability. And then we're trying to use that quantified variability to turn that into a probability of how good our measurement is. And that's where we're at. We've worked out that if we use as a measure of variability, if we use the standard deviation, which is almost the same as the measure of variability we come up with on our own, but if we use the standard deviation, then that relates to the distribution of variability that we might see from random processes. And that we're assuming that we've got random processes that are causing the variability in our measurements. So we're putting those things together, and essentially if you've got the spreadsheet that you downloaded at the start with this data on it, that's the completed version with the frequency distributions for the students, and also you working out your measure of variability yourself, and then here you're comparing it. If it wasn't clear, there's these two values here. This is the standard deviation as worked out by you, and then that's the standard deviation function in Excel. It's just for you to compare the two, and you can see they're the same. The reason I've sort of gone back to this when you're hoping with moving forward is that when you use Excel, it's really important to recognise there's more than one standard deviation. You'll have seen that when you type it in. The standard deviation P, standard deviation A. If you just use standard deviation, STDEV, then that's fine, you won't have a problem. The thing that comes up is standard deviation P. Standard deviation P is when actually you're measuring the standard deviation of the whole population. You can think about it, it's unlikely that you'll ever do that. If you could measure the whole population, then you know there's lots of other things you could do. But standard deviation P is just a thing to avoid. There may be very occasionally time you might use it, but don't use it by mistake. STDVP. The difference in the formula is that for the standard deviation, you divide by the number in the sample minus 1, whereas for standard deviation of the population, if you assume you've measured everything in the population, you don't divide by n minus 1, you divide by n. So it makes a very slight difference, but just as a little warning to you. So particularly in this, where there might be a few simple calculations to do as part of your short answer multiple choice test, in order for your numbers to come out right, you need to be using the right standard deviation. So standard deviation P has a purpose, but it's quite rare for you to be using it. And it's just with Excel, you know, sometimes it kind of fills in automatically if you type stuff in. So the standard deviation. If you just write STDV, it will let you do that, but it might say this belongs in Excel 1984 when Dr. Bolt was first using it, but it still uses that. But try and give you a letter after it. There are other versions besides P as well, but just make sure you don't use standard deviation P. All right, so that was the purpose of this spreadsheet. So you come up with the standard deviation on your own. Then this is the one where we left it, which was, this is the Gaussian distribution. Okay, and it's drawn using these two columns, so notional height and the frequency. So the formula in here is the Gaussian formula. So all we're doing is drawing a Gaussian distribution. Up here are the inputs for it. So we've got the size of the population. This is just a model to show what's going on. So we're saying the size of the population is 1, actually, and we've got parts as 1. The mean is 0.5, the standard deviation is 0.15, and you said height, but it's a variable. I mean, there aren't any people that are 0 meters high, or in fact 0.04 meters high. It's not really height. So this is the parameter that we're interested in. So if we were to change the standard deviation from 0.15, if we were to make it 0.25, what would happen to the shape of our curve? You can all use your hands to show me. Right. Go on, use your hands. Show everyone. So it used to be a dance in the 1990s, but not anymore. All right. Look, we'll do it just for fun. Let's change it to 0.25. Just as a little aside here, does anybody on their computer, like on your keyboard, you have a keypad on this side, does anyone not have the keypad turned on? Like, you don't even see it. It's a stupid question, isn't it? You think, how could it not be turned on? Like normally on this side, you have numbers and you can type numbers in. Every computer I come to use, like that keypad's turned off. That's why I keep having these problems. So I'm typing on this keypad and it's not putting numbers in. I've wasted even more of your time telling you about my problems, but that's it. So 0.25, we'll put that in. There you go. Another problem as well that I should warn you about, which is important, the other spreadsheet that I showed you, this one, we'll come back to this as well when we move into the sort of modelling bit, but it's using Excel in a different way, and it's not doing automatic recalculation. We'll talk about this when we do it, but the net result of it is that if you open, and it's important to show you this, because if you open one of the spreadsheets, like if you were to open this spreadsheet, if it was the first spreadsheet that you open in Excel, then it adopts all of the options that are set for this spreadsheet. And the options that are set for this spreadsheet are manual recalculation. It's important because we're using it in a modelling way, okay? Which I'll explain later. But it means that when you type something into Excel, it doesn't change straight away anymore. You have to press F9. So it's a useful thing for you to remember. If you find that your spreadsheet isn't responding, and you're getting angry with it, as I was, then try pressing F9, because it's not automatic anymore. And it's a warning to you, because some of the spreadsheets that I'm going to get you to use are set up like that. And if they're the first ones that you open, then the rest of your spreadsheets won't work in the way you're used to them working. And you can either close Excel down and open it again, or you'll have to press F9 every time you use it. So anyway, so the net result, when we change the standard deviation to 0.25, and the distribution spread out. All right. Just change it back. So, I'm looking at the slide. And press F9. And so what's going on here? Your spreadsheet doesn't have these numbers filled in. This is your job to fill these in. The point being that this is the distribution of variability, if the variability is wholly caused by random processes. That's what we'd expect the distribution to be like. So if we measure the standard deviation in our sample, and we assume that the variability is caused by random processes, then what we can do then is to work out how likely our measurement is to be a true measurement. So the way we do that then is, if we have, let's say, you know the standard deviation. If we plot the standard deviation on this graph, so the way our thing is set up, the standard deviation, if you have standard deviation, one standard deviation, so measure the standard deviation, you plot it on the graph, and the standard deviation is 0.15. So from the middle here, this is 0. If we go 0.15 this direction and 0.15 in this direction, so from 0.5, if we add 0.15, we go to 0.65. If we take it away, we go to 0.35. And then that area that's within one standard deviation of the mean, we want to know what percentage of the whole of the area of the curve is covered by one standard deviation away from the mean. And that's what you're filling in here. So over here, we're going from 0.36 to 0.62, sorry, to 0.64, 0.36 to 0.64. Really, we want to go from 0.35 to 0.65, but the resolution's not high enough. So we're filling in this, and all we're doing is working out the area here. If we add all these together, it'll give us the area between 0.35 and 0.65. And the sum of that is at the top there, which is 0.68. All right. Some of these numbers should start to feel familiar to you. Right. The number that you should all know is 95%. Actually, let's say, yeah. What? Right, I don't know which numbers you've been told, but in order to have 95% confidence, this is something you'll have heard before, how many standard deviations away from the mean do we go? This is a number that you will have heard, and we're going to see how it matches up. Anybody? We've got 2 at the front. What have you got? 0.3? Right, I thought that I came from the Dark Ages, but see, 2 is the approximate answer. 1.96. People, 1.96 really should be a number that's in your minds. Let's get this one. 1.96 actually, it's 1.96 standard deviations from mean, so we're trying to see how that matches up. As it happens, it's close to 2. 2 standard deviations from the mean is giving us 0.96. 0.96 of the distribution is covered by 1 standard deviation. Okay. By 2 standard deviations. 2 standard deviations away from the mean, we're covering 0.96% of the whole distribution. And that's how we come up with the statement that we can be 96% confident. If it's 1.96, it's 95%. Okay? So the idea is for you to just fill this in yourselves to understand what's going on. So you can see that all we're doing is taking the frequency, which is the height here, multiplying it by the size class, so that's by the distance. So we're multiplying the height by the distance to get the area. That's all that's going on. In here, I've taken this number, D25, and I've multiplied it by B5, which is the height. This is the horizontal distance, which is the size of the class. So multiplying the horizontal by the vertical gives me the height by the width, so I get an area. And then all I'm doing at the top there is to sum those together. It's the sum of those. And then I divide it by the number in the population, which in this case is 1, because we set it up as 1. And then if we do that, we actually produce our own statistical table. So we're at the point then where if we know what the variability is, and we use the particular measure of variability we use as a standard deviation, then it allows us to start giving quantitative estimates of how likely our mean is to be the true mean. And that starts to be suddenly, actually, to know what that's actually useful. That's a useful thing to do, rather than just, I've made a measurement. If you start from this premise that any measurement you make isn't a true measurement, then it really is like, what's the point of doing any of this? You might think, well, it's a lot of point. I could measure this desk once and tell you the measurement, and actually, if you went and bought a tablecloth to go on it, actually you wouldn't be far wrong. Okay? But you've no idea. There's lots of assumptions in that. When I say I've measured this desk, you're assuming that I've measured it with a ruler that's got the resolution of centimetres, but that might not be the case. I might have measured it with a ruler that's got the markings on the ruler are like 6 metres apart or something, and you've got no idea of like the quality of the measurement at all. So you have to sort of approach measurements on that basis. Like you don't know anything about the quality of it, which kind of leads to the point that really any number that you're given is a meaningless number unless it's followed by a percentage of how likely it is to be the true number. And we should really start with that as our default condition. It will also make you look like the smartest person in the room, but also people will hate you. Because it's always something that you can criticise, because you can do it to me, because I'm going to give you some things to do and actually there won't be some errors on them. And because you're all polite, you don't throw it back at me, but you could do, and you'd be right. You're always right if you say, where's the error on the number? So if you're feeling defensive and you want to look smart, then just come up with that. It's that balance of being right and being a pain in the arse. You decide which it's best to be, but there's certainly times when it's best to show that you're smart. But it does matter. Like, you don't know, you've got no idea about the quality of the number. And it will matter a lot when you do your thesis, because it's such an easy thing to criticise. When you present the data, no one's got the time to mark these things, and everyone's doing it under sufferance. The easy thing is to go and look at the numbers, and you can say, well, actually, these guys, there's no errors on the numbers, and they'll always be right to say that. So this is the point. Really, we can't separate the number from the error that goes with it. We haven't quite finished with this, though. This. Those numbers, the 1.96, which is the number of standard deviations to give you 95% coverage of the distribution, is a d-value. So you'll see it referred to as a d-value. So if you've got a confidence level, the number of standard deviations that goes with that is the d-value. So the d-value is 1.96. We should finish off really what we're doing with this. It's two. All right, let's say we've got to the point there where we understand what the d-value is. Now, we haven't quite finished yet in our comparison of one thing with another. We're almost there, but we should just finish it off, and then we can do something that's maybe slightly more interesting. But we just have to jump ahead. what you're actually going to be doing most often is comparing then the means of multiple measurements. We've gone a long way towards being able to do this. So the example you're going to deal with is whether two different sites are, which one is more contaminated than the other. So we've got multiple measurements of contamination at two different sites. And we want to know, is one site more contaminated than the other? From what we've done then, it appears we're now able to make measurement useful because we related the sample mean to the population by a probability of their coincidence. All of this assuming that the distribution of the errors is normal. We'll come back to that. You've got to consider, the things we haven't considered at the moment is, well, there's two things there. The second of them is clearest. We haven't considered the sample size. So at the moment, it doesn't matter what the sample size is in terms of us coming up with a confidence in our measurement. You know, we come up with those d-values, which would allow us to have a certain quantifiable confidence in our measurement, but sample size hasn't fed into that. So one of our sets of multiple measurements might be 50 measurements and one might be 3, but we've got no way of distinguishing the confidence in each of those measurements. So we actually need to bring that into our calculation. At the moment, we're using the standard deviation, but that's the standard deviation and the d-value. But it says here, it seems reasonable that confidence should be greater for a sample mean drawn from a larger sample than a small sample, which is what you two guys said right at the start of this. But that's not, it's not part of our calculation at the moment. To do this, the d-value's got to be modified. So we need to change the d-value. And the way that we change the d-value is that if we've got small samples, then we don't use the d-value. We use the t-value instead. Okay? Which again is something that you can just look up, but we're using t-values, not d-values. The way to think about this then is we're trying to assess 2 points. We've made multiple measurements and we've worked out the mean value. We'll see this as an example here. Let's say we've worked out the mean value of copper concentration. We're looking at heavy metal pollution, actually measured in seaweeds. And we've got two sites. We've got site A and site B. Okay, and the mean value at site A is higher than the mean value at site B. Now, for people that weren't scientists, then the answer about is site A more contaminated than site B? The answer is yes, site A is more contaminated than site B. But for us, we know that doesn't make any sense because we know these measurements, we can't make true measurements. So to just give a measurement and say this one is different to this one or this one is greater than this one doesn't make any sense to do that. So we're going to quantify the variability. Our first go at doing that is we measure the standard deviation of the multiple measurements. So as well as calculating the mean, we also calculate the standard deviation. Then we need to make a big decision, which is something again we'll talk about, but we'll just move quickly over it, which is we need then to decide how confident do we want to be that these measurements are different. And the standard thing is we work at 95% confidence. So with the two measurements, we've decided that we want to know that we want to be 95% confident they're different. So we make the answer to are they different, we want to say that to 95%. So we know it's 95%. So we know then how many standard deviations on either side of the mean do we need to consider? What's the answer? Help me out. How many standard deviations for 95% confidence? 1.96. Brilliant. So let's say we measure the standard deviation on site A, and the standard deviation was, I'm going to put my number back, right, was 3. Okay, so the standard deviation was 3. The copper concentration was 15 milligrams a gram. The standard deviation was 3 milligrams a gram. 1.96 times 3, let's say it's 6. Okay, so our error bar, which is what we draw on there, would be 6 milligrams above 15, so it goes from 21 to 6 milligrams below 15, which is 9. So between 9 and 21. Our other point is actually at 12 milligrams a litre. We've got the mean is 12, the mean at site A is 15, the mean at site B is 12. Right? We've drawn our error bars on this one. It goes from 21 to 9. We're going to draw error bars on this one as well. Let's assume they're pretty similar. The fact is that the error bar overlaps with the sample. Okay, the error bar overlaps with the sample. The error bar on this one extends down to 9, and the mean on this one is 12. And that's not even including the error bar. So, because they're overlapping, we can't say, we're not 95% confident those two means are different. Okay? And that's a joyous thing to be able to say, because it means we don't have to say, oh, they might be different, or it's possible they could be different. The reality is, as far as our level of confidence is concerned, is they're not different. However, right, we said that if we've got small samples, we shouldn't be using the d-value. The d-value is 1.96. But the d-value, what's the size of the sample that the d-value assumes that you've got? Remembering the only question I ask you, the only answer I expect from you. How big a sample? In order for you to really be justified in using the d-value, how many measurements do you need to make in your sample? Is it 7? Is it 13? Is it 111? Infinite. Right, in reality, it should be an infinite sample size. In practice, well, you tell me, because this is a number you'll have heard, but maybe there's different numbers in different countries, but what's regarded as a small sample size? What's it below? Yeah, that's what I've heard as well at school as well. We've got a below 30. If it's above 30, then you could use the d-value. Has anyone heard any other numbers in their travels and education? Generally it's 30. If it's 30, then you could use the d-value. One of the things you can do is actually you can check the difference yourself between using d and t for a sample size of 30. There's still a difference, actually. So the 30 thing applied when it was a bit more trouble to actually look these things up, but now you've got computers. You're better off using the t-value if you've got really a sample that's less than a few hundred, probably. So let's see what's going to happen then to our argument. We've got our site A at 15 and our site B at 12. We've got the error bars drawn on there. And the error bar that's drawn on there is assuming that the number of samples that was taken was infinite. We know that it wasn't infinite. In fact, it was 3. Okay, it's a triplicate sample, which is a typical thing. So it's less than 30, so we should be using the t-value. So the d-value was 1.96 times the standard deviation. What do you think the t-value is going to be? Is the t-value going to be larger than the d-value or smaller? Imagine what's going to happen to your error bar. So I'll let you think for 5 seconds and then we'll have a show of hands. Right, that's 5 seconds. So the t-value then, we want a t-value. Is the t-value going to be larger than 1.96 or smaller? Put your hand up if you think it's larger. Put your hand up, don't be afraid. Come on, Philip. Right. Who thinks it's going to be smaller? Right. There's a lot of people that really aren't playing the game, but there you go. It's going to be larger, isn't it? Because we're going to have less confidence. So really we're going to expect our error bars to get bigger. And that's because the t-value will be larger than the d-value. Okay, so it reduces our confidence. And actually the t-value for 3 samples, which is 2 degrees of freedom, at 95%, is 4.303. Okay? Whereas the d-value is 1.96. So it's more than twice as big, okay, by having a triplet sample. So come back to our argument now. We've got our 2 points. We're trying to say whether they're different or not. We've plotted our error bars on the standard deviations, which I can tell you in at least 2 theses that I've looked at this time, people plotted error bars as the standard deviation. Okay? Which, I mean, they did say it was a standard deviation, but the point is, like, what does that actually mean? Like, that didn't really mean anything. I mean, you could get an idea of the variability, but for me to say whether I could be 95% confident that points were different to each other, plotting the standard deviation didn't help at all. It wasn't even the d value times standard deviation, just the standard deviation. But anyway, we plotted the d value times standard deviation, but error bars like this. We recognise we need to take account of the sample size. We do that by looking up the t value. In order to get a t value, we need to say what the sample size was. And it's normally in terms of degrees of freedom, which is the number in the sample minus 1, and the confidence level we're working to. And suddenly our error bars go like this. So we're even less able to say these two samples are different. The one other thing, though, is there were 2 things that had to be considered. One was the size of the sample. So the size of the sample has made our confidence less in this case because we've got 3 rather than an infinite number. But the other thing we need to consider is that we're looking at the variation of means rather than the variation of measurements. So we're comparing 2 means to each other, not just single measurements. And the result of that is that actually we should be looking at the standard error of the mean, which means that the standard deviation can be divided by the square root of the number in the sample. Okay? That's because the variability of means is less than the variability of samples. You can look at this yourself, because it's suggested that you could do that. With that list of student height data, there's 500 students in there, and you plotted a distribution up and measured the standard deviation of the whole of the sample set of 500 students. If you broke that down into groups of 10 students, so you have 50 groups of 10 students, you have 50 means of the 10 students. If you plotted up the distribution of those 50 means, you'd see the distribution was much narrower than the distribution of all of the sample. So if the distribution of the means is narrower than the distribution of the sample. And that's kind of working in our favour, if you like. So we're doing 2 things to our starting d value. We're happy with the d value to give us a confidence limit, but actually we had to take account of the number in the sample size, and that meant that our confidence limit grew because we used t rather than d. But actually, because we're looking at the variability in means rather than of samples, then we're actually going to look at what's called the standard error, which means we divide the standard deviation by the square root of the number in the sample. So the standard deviation, even though d's gone to t, which is larger, the standard deviation is going to get smaller because it's the standard error that we're looking at. So our error bar then, through this argument, has gone from being it's like this, it's gone like this because we've gone to t, and then it's gone back to something like this because we're looking at the standard error of the mean. And that would be a term that you've heard of, the standard error of the mean, right? But we're not plotting the standard error of the mean. If we were plotting the standard error of the mean, we'd get the standard deviation, we'd divide it by the square root of the number in the sample. And that would be what we're plotting. But again, that's really not that useful to us. We want a confidence limit. We want to say between these bounds, we're 95% confident that the number's between these bounds. So ultimately, what you need to plot is a number with a confidence limit. You can plot a number with the standard deviation on there, say that you're doing it, but you have to think, what's the point of doing that? If I'm comparing 2 numbers, what I'm going to be saying is the standard deviation is different. What we want is the confidence limit. You can plot a number with the standard error on as well, which people sometimes do, but again, it doesn't mean that you can compare those 2. Confidence limit is what we want to end up plotting. And to plot the confidence limit, we need to work out the standard deviation, we need to get a t value, and we need to turn the standard deviation into the standard error. And the formula for doing that is, it's all there for you to do that. And there's several examples for you to do that. And by doing that, we can then say whether we're 95% confident these numbers are different. And fundamentally, like you'll have done t-tests as well, the same mathematics is going on in a t-test. They are functionally the same as what's going on here. Right. So that's us then able to plot confidence limits. That's what you can sum this up as, it's confidence limits. So when you see CL written in capital letters, it stands for confidence limits. And they're normally expressed as plus or minus, or as an error bar. So on a graph, you'll have an error bar, and it will have an error bar going up, which is the plus side, and down, which is the minus side. If you're writing them down in text, then you'll give the number, and then in brackets afterwards, it will say plus stroke minus, and then it will give the number. Somewhere in your text, in your figure legends, you should explain that the confidence limits are drawn at 95%, if they are. Typically they are at 95%, but you should say somewhere that's the confidence level you're working at, because there are times when you work at different confidence levels. You should say what the error bars are. And if they are confidence limits, you need to say that confidence limits are drawn at 95%, or whatever the percentage is. Make sure that's written down. Yeah, there's an example there for you to do. And let me... Right. Right, we've made... What you might think we've made a very big deal of this, because I've spent a lot of your time and you've looked at all this and everything. It's not a big deal, because it's really central to what we do. And you'll see the same argument going on in other things that we do. So it's worth doing this. And when we see how much trouble we go to actually not just give a number, but give some confidence on it, then the next thing that you would ask then is, well, what do we do with those numbers when we need to add them together or multiply them? And the answer can't be we just forget about them. After you've got all this trouble, in the first place you've made multiple measurements, which means you've done at least 3 times as much work as you would have done otherwise, often many times more. You do all that work, then you actually work out the statistic to go with it. That error, we said, the number itself is fairly useless without the error with it. And if those errors disappear when you start to do calculations with the numbers, then that's even worse. So we need to know what to do with the errors when we actually do calculations with the numbers. And again, you can make yourself look like the smartest person in the room by making sure you always do this. So this is propagating errors. So that means if you're adding 2 numbers together with errors, what do you do with the errors? If you're multiplying 2 numbers together with errors, what do you do with the errors? The best thing really is that you need to read through this, and there's a little exercise to do. Just make sure that you do it. You will recognise, like for adding the errors together, what you end up doing is squaring the errors, adding the squared errors together, and then taking the square root of them. Right? Some of this, it should have a sort of vague familiarity, you know, in as much as like you've been squaring things before to get the standard deviation. And that's, if we went into the mathematics of it, it actually involves solving second-order partial differential equations, and we're not going to do that. We're not going to go into the maths of how this is done, but there's a link there to the standard deviation itself. So if you're going to add 2 numbers together or subtract 2 numbers, then you square the errors and add them together and take the square root, and that gives you the error of the addition or the subtraction of the numbers. And for the multiplication, it's only slightly more complicated. For the multiplication, you take the error, divide it by the number itself, and square it. And then you do the same for the other number you're multiplying by, square that, add those together, and take the square root of them. And that gives you what's called a fractional error, which you then multiply by the resultant quantity. The resultant quantity being the 2 numbers multiplied together. So it's just, for the multiplication, you're scaling the error by the size of the number. And that's why there's another step in it. The easiest thing to do is just follow this through. Have a look at this, do it yourselves. And there's an example for you to do, which is down at the bottom, propagating errors. The example, again, it's a real example, and it's to do with discharge consent. Right? Polluters are given a consent to discharge by the Environment Agency. They are allowed to discharge a certain amount of pollutant, and the exercise is for you to see whether they're actually within their limits or not. And the consideration really needs to be the limits actually have got an error on them. So you're going to work out the amount of pollutant discharged in a period of time and also the error on that. So the pollutant is being discharged into a river, so you need to know the flow of the river, the concentration of the pollutant. To work out the flow of the river, you need to know the width and the depth and the velocity. Each of those have got an error on them. So you're multiplying things together. So when you do this little exercise, it does say to you, actually, there's a text box in there. It tells you the first thing to do is just work out the numbers first of all. Forget about the errors, just work out the numbers. Okay, we're doing this several times again, really, working out pollutant fluxes. In order to do that, we need to work out a discharge. So you need to multiply width by depth, and multiply that by velocity. And keep an eye on the units when you're doing that. So when you're multiplying the widths in metres and the depths in metres, then you get square metres. If you multiply square metres by metres per second, which is the velocity, metres per second by square metres, you end up with metres cubed per second, which is the discharge. And then you've got a concentration of the metal that's being released. The concentration will be in mass per metre cubed. If you multiply mass per metre cubed by metres cubed per second, then you end up with the concentrations per time. Ultimately, you want to end up with a mass over time. So just keep an eye on the units when you're doing that, and then you can track the errors through. So it's important that you actually just go through and do that exercise for tracking the errors through. Okay. Right. So far we've been talking about the normal distribution really as part of, really as a statistical thing for allowing you to compare numbers one to another. So we've been talking about it really for statistical purposes. However, it's also very useful for modelling physical processes. You may have made that connection already, because you've seen the physical process of these particles moving. That's where we got this model for the normal distribution. It's particles moving due to random processes. Much of the movement that you get in the environment ultimately is effectively due to random processes, things that effectively are indeterminate. So for the way that pollutants move, a very important process for pollutants to move is just dispersion, which is the random movement element. Okay? Ultimately, if you're looking at the way that contaminants are dispersed in the atmosphere, for instance, largely the atmospheric movements in the lower atmosphere are turbulent, which means they're random. There may be a wind direction as well, but on top of that, there's random movement, just random movements of the air. And from what I said this morning, actually, you know quite a lot now about trying to predict how pollutants might move, because we've got an equation that models random movement. The Gaussian equation models the results of random processes. That's useful for us in that we're generating effectively random numbers every time we make a measurement. But actually, it also has a physical importance, because the way that pollutants might be moved around is due to these random processes. So there's an example of this on the spreadsheet that I've given you. And what I just said is explained here as well. So, as usual, where's it better explained? Probably better explained here. The normal distribution is valuable statistics, the set measurements in their context of natural uncertainty. It's possible because it models acausal variation. The ability to simulate acausal uncertainty means it can also be used to predict the behaviour of real physical systems, which are controlled by acausal processes. Whilst processes controlling environmental systems may not be strictly acausal, they are effectively so because their subjects are controlled by multiple interacting variables. There's a whole lot to think about in what I've just said there. Lots of the work that gets done here is picking apart things that seem to be acausal and effectively random. If you look into it more and more closely, you can start to come up with a deterministic model of what's going on. So I'm saying that, we look out here and you can see the air's moving around randomly. My atmospheric scientist colleagues measure those random air movements very, very closely in their micrometeorology and work out exactly why the air's moving in the way it's moving. However, generally in these environmental systems, there's so many different processes interacting. The net result of that is that it's an acausal process. You can't work out what's going on. So it's effectively a random process. Simple models and predictions of dispersion in the environment take advantage of this. The best example, and one that's got analogies in several types of environmental systems, is diffusion. So diffusion of dispersion is basically modelled by using the Gaussian equation. So lots and lots of models you use in a consultancy, that you use at work, things that you do in projects, start off with assuming you've got random movement and you can model it using a Gaussian equation. Molecular diffusion is the continual redistribution of molecules in a fluid. Motions result from the heat energy, but direction is a function of collisions. That's why it's effectively random. So heat causes the particles to move, but depending on what they hit is going to control the direction they're going. What they hit one time, they hit something else the next time. You can see how it actually ends up being a whole load of random movements. Because of the very large number of molecules involved, if observed at the macroscopic scale, these motions are effectively random. The distribution of molecules, e.g. cadmium or copper or something discharged into a lake, can be predicted directly from the normal distribution. The process by which diffusion occurs is described by Fick's law. The diffusive flux is proportional to the concentration gradient. In other words, the rate at which particles move through a measuring point is proportional to the differences in concentration on either side of the point. Now, I think both of those things are things that you may have heard of, okay, a bit, at least, and some of you a lot. But actually, we've described two different things there. We've said that diffusion is a result of random processes and therefore it can be modelled by the Gaussian equation. And we also said that diffusion is driven by a concentration gradient, which is Fick's law. So you've got two different things there. And the exercise that I've set up for you is for you to show that both those things result in the same thing, i.e. they're both true. So you'll have heard diffusion described as being a random process, and therefore to be modelled by the Gaussian equation. You've also heard that diffusion is controlled by the concentration gradient. And just to explain that a little further, just in case people haven't come across it before, the idea would be you've got a very high concentration here and a very low concentration here, then the rate at which material moves from here to here is quite high. You can see what happens then as the material moves from here to here. You start with this big concentration gradient. As the material moves, the concentration increases here and it decreases here. The concentration gradient then is decreasing. So the rate at which the material is moving is also falling. So we could plot the concentration at 2 points that are separated. It starts high over here and low over here. We plot those. If we also plotted the rate of diffusion over time, so this would happen to the concentrations, they'd do that. What would happen to the rate of diffusion? So against time, like this, so the rate of diffusion would be high to start with, wouldn't it? Because the concentration gradient is really high. And then over time, it would drop. And when you end up with the concentration the same at 2 points, then the rate would actually be 0. So it would drop from being high to being 0. Okay. So that's a description of Fick's law. And we've also said that diffusion is controlled by random processes. So it should also be described by the Gaussian distribution. So if we look at your spreadsheet, which is this tab on that spreadsheet that I've given you, the object of this is to show that materials subject to diffusion will be distributed normally. So the process of diffusion we've described by Fick's law. So we want to use Excel, use a computer to simulate Fick's law. So that's one thing we're going to do. We're going to simulate Fick's law using a computer. And then when we get an output from that, an output from our model of diffusion using Fick's law, we want to compare it to the Gaussian distribution. The point being that the two should overlap, because we said it's the same process. And that's really what's going on here. So we're going to plot starting normal distribution, which is what we're going to compare our model output to. So we do a starting normal distribution, which is drawn for you here. We're going to let diffusion operate on that normal distribution. So we're going to start off by producing a normal distribution of concentration. You can think about it as the concentration of, what's your favourite pollutant? What do you fancy? Phenol is one of mine. I like phenol. You could say phenol. Nasty, nasty, nasty organic contaminant. We've gone and poured a big barrel of phenol in a lake, in the middle of the lake, and we're producing the concentration profile across the lake of the phenol. So it's really high where we poured it in. To start with, the concentration profile looks like this. It's a big spike of phenol in the middle of the lake. Sorry, I'm spitting at you. And not very much or none at the edges. All right? But you can see the normal distribution will be like this. The phenol will be highest at the centre of the lake. So imagine that's what we're looking at. So we produce our starting concentration profile of phenol across the lake. And then we're going to let Fick's law operate on our starting concentration profile. We know that the concentration is high in the middle of the lake and it's low at the edge of the lake. So we know that there's going to be fairly rapid flux of the contaminant from the middle to the edge. We want to see that develop over time. Now, in environmental modelling, we'll talk about this more later on. Typical way of doing environmental modelling is that we break continuous variables into discrete units. If we don't do this, then it means that we need to solve very complicated differential equations. Right? Even as I say it, I'm saying to you, we don't do that. We don't do that. Right? Some people do, but largely we don't, because in the world of computing, we can do things differently. But the starting point is that we break continuous variables. We talked about continuous variables already, but we break continuous variables into discrete units. So the continuous variables we're interested in are distance, because we're interested in the concentration of phenol across a lake. We know that distance is a continuous variable, but actually we're not going to deal with it as a continuous variable. We're going to break it into pieces. The other variable we're interested in continuous is time, because we're interested in how this concentration profile develops over time. Time, as we know, is a continuous variable, unless I were to do my robot dance and everything, so I'm not going to do that. Time is a continuous variable, but we're going to break that into pieces as well. So that's why this is a sort of very, very simple introductory exercise, but the fundamentals behind it apply to almost all environmental modelling, all computer modelling. It's breaking continuous variables into discrete variables. So if we see what's actually going on in here, this is the starting distribution. It's got height written there, but really by height we mean concentration. So we've got concentration, and we've got This is in concentration. So this is distance. Height is the distance across. Frequency is concentration. You can read frequency as concentration. It means the frequency of particles in a volume. You know what they're in there? So this is the concentration. And the starting values are these ones. These values have been calculated using the normal distribution. So if I click on there, well, you can't see it, but the equation in there is the equation for normal distribution. We know the parameters for that are the mean and the standard deviation. And we're drawing this, and it's actually this blue line. You can see here. We've got this bell-shaped curve here. That's our starting concentration gradient we put in. And we're reproducing that here for us to carry out. This side of it is our model of diffusion using Fick's equation. Okay, so this is letting us look at the progress of diffusion over time. This is how we're getting our starting concentration profile. The equations that are in here then, very simple. We've got the concentrations here, and then we're working out the flux. And all we're doing is what we said, which is the flux is proportional to the concentration gradient. The concentration gradient will be the difference between this concentration and the concentration next to it, divided by the distance between the two of them. So the gradient is the difference in y divided by the difference in x. And that's all that's going on here. So the equation that's written in there is E26 minus E25. So that's the difference in y. Okay? And so that gives us the gradient. And the gradient is proportional to the flux. So because it's proportional to the flux, we need to also have a diffusion coefficient. So the rate at which the material moves is proportional to the concentration gradient. It's equal to the concentration gradient multiplied by a coefficient, the diffusion coefficient. So that's E22, which is written up there as well. So that's, yes, sorry. Here where it says KD, that stands for diffusion coefficient. These are just arbitrary numbers that I put in. The diffusion coefficient is set as 20. So that's how we work the flux out, because the flux is proportional to the concentration gradient. So we've got a column there that says flux. What we do with that flux, though, we need to subtract the flux from the starting concentration. We're saying that the material is moving, so if it's moved, then we need to subtract it. So as time goes on, we're subtracting the flux. So in each time step, we're subtracting the flux, and that lets us come up with the new concentration. So you've got a concentration, we work out what the flux from that cell is, and then we subtract that flux and we get a new concentration. So the point that I was making is that we've broken down distance into pieces. Distance isn't continuous anymore. And because the distance isn't continuous anymore, then the gradient isn't calculated by calculus from the equation. It's actually calculated just by differences between each of these cells. So we do that, and then time also is broken down. So where it says T1, that's the first time step. So we're letting time run in small periods. It's not defined what the period is, but you would define the period. So time 1, time 2, time 3. Between each of these, we're generating a new flux and then subtracting the flux to get the new concentration. We use the new concentration to work out the flux, and then we subtract the flux to get the new concentration. And if that's not clear, it's because I'm not explaining it well enough. But it might also be that it's simpler than you think. Right? Because there's a complicated thing going on here. This is really, like, you could use this model. You know, if the lake didn't have any wind blowing over it, you could use this. This is really a pretty good model of what goes on, just down to diffusion. And we're not having to do any differential or integral calculus to do this, just because we've broken time into pieces and we've broken distance into pieces. The problem comes that in order for us to get something that really does simulate the environment, the number of pieces that we break time into, or the number of pieces we break the distance into, needs to be, ideally, how many pieces do we need to break time into?
Infinite.
Yeah, it needs to be an infinite number of pieces, right? And the distance needs to be an infinite number of pieces. So there's a problem there, because we're not going to break it into infinite number of pieces. And we'll see that actually in this example. This example, though, is done on a computer. It's not really using tons of computer power, right? So there's some problems with the resolution. But if I just back out of this so you can see a bit better now. So this is what we end up with then. So this blue line here is the starting distribution. Don't be confused by that. You could say, the starting distribution could have just been a distribution that's like this, just a point. If we pulled the barrel of phenol in, the starting distribution would have just been a line straight up. And we could have worked from there. But we've done it with the normal distribution because in the end we want to make a comparison to that. That's the ultimate objective of this. You can see we're covering lots of things in this, but the ultimate objective is to show that the model of diffusion by Fick's law results in the distribution that aligns with the Gaussian distribution. And just showing the two things match up. So we're starting off with this then, the blue one, and then as time goes on, T1 is the yellow one, T2 is the light blue one, and then T3 is the next one. And we could carry on, and this would flatten out more and more. Okay, so you can see that's going on. The question that I've asked you to answer is, repeat the simulation to show the passage of time. So I think in your spreadsheet, like T1 to T5 aren't filled in. You can fill those in to see how it changes over time. Compare the distributions produced by simulation of diffusion to that produced by increasing the standard deviation. So this red box here, you can change the standard deviation of the normal distribution. So compare the distributions by simulation of diffusion to that produced by increasing the standard deviation. Is diffusion over time equivalent to increasing the standard deviation in the Gaussian equation? Like for us to say that Fickian diffusion produces an output that matches the Gaussian equation, we just want to see those two lines overlapping each other. Okay, so you're producing these lines by letting time run on from your Fickian process, and you can change this standard deviation in order to try and get a Gaussian distribution to plot right on top of one of those lines. So the question is, what are the values of standard deviation that are equivalent to the distribution after diffusion to T1, T2 and T3, the 3 decimal places? So trying to get you to change the value in the red cell, which is the standard deviation of the normal distribution, change the value in that cell so that the blue line drops down and plots on top of the yellow one, plots on top of the blue one, plots on top of the purple one. And the point is, if they do plot on top of each other, then that shows you one of those lines is being produced by using the Gaussian distribution, which models random processes, and the other one is being produced by Fickian diffusion. And you can see that the two things match. Okay, so that's just an exercise for you to do. But in doing it, you need to understand the way that spreadsheet works. And actually understanding the way that spreadsheet works is really the fundamentals of lots of environmental computer models. So that's why we're doing it. And another thing you'll notice here, as we get to the edges, we get some weird behaviour. You can't see it back, but the edges, look, this goes up and down. Those problems with the edges are due to the resolution of the model. You know what I'm saying to you? We've broken distance up and we've broken time up. ideally into an infinite number of pieces, but we've broken up into not very many pieces at all, really, for this kind of model. And you see the effects of that just at the edges where the model goes wrong. Okay, so that's what's going on there. Okay, so have a look through that. Okay, do the exercise, but in doing the exercise, let's just start to think about. There's a recording of this as well. We'll be coming back to these points, but I'm hoping that you can see that they're kind of linked together. You know, we started off talking about continuous variables in order to do the most basic statistics, which some of you think I've done this before. I hope that you've got a really clear understanding of why we do those things now, but also, like that thing about continuous variables links into the more complicated environmental modelling that we do as well, because largely using computers, which is the way we do this, relies on breaking down continuous variables into these discrete variables. You can see that happening. We'll do some other examples of that. When you're in work, there'll be big models that you won't have written them, but inside, this is all they're doing. You know, and I was saying to you at the start about computers as well. They're not clever. They just do simple things really, really fast. And you can see that's what's going on here. You know, the complicated, clever thing to do would be to solve the equation for the shape of these lines. Right? Solving the equation, it normally means integrating an equation. We're not doing that because we've got rid of calculus. There's no continuous changes. Calculus involves continuous changes, but we've said, no, we're not doing that because we've broken the world into discontinuous, discrete changes by making time go in steps and making distance go in steps. I'll talk about this more, actually tomorrow. I'll talk about this more tomorrow. But it's not because we're stupid that we don't do that in maths. It's because the equations that you get for environmental systems, we can't solve those equations. You know, I mean, I'm really not that good at solving partial differential equations at all. However, the ones for environmental systems, nobody can solve them, so we have to deal with them in a different way. All right, just the last thing to finish off. I know we've gone over our 50 minutes, but we'll just spend a few more minutes and then we've finished. There's another exercise here as well, which is worth doing just to show you the magic of these statistics, which is that you can calculate how likely it is that there's a 7-foot-tall student. So from the data you've got of these 500 students coming into the building, we didn't measure a 7-foot-tall student. We didn't see one. But with the data, you could calculate how likely it is that you could see a 7-foot-tall student. And that's a little bit magical, really, in a way. You know, it's like, I've never seen a unicorn, but I can tell you how likely it is that there is a unicorn. That would be exciting, and in this case, we didn't see a 7-foot-tall student. In fact, when we actually made these measurements, there was a 7-foot-tall student who was doing the class, but I've never seen one. But you can work out the likelihood of it, and you can see how that would work, because if you've got the standard deviation and the mean, it means you can draw a normal distribution. If you could draw the normal distribution, the edges of that normal distribution, they never actually hit the x-axis. They're asymptotic to the x-axis. They don't hit the x-axis. So the heights that you can go to, actually, how tall could the tallest student be if they were normally distributed? They could be infinitely tall. Okay, and that's clearly ludicrous, but we can balance that out by how often would we see an infinitely tall student? How rare would they be? How rare would they be? Infinitely rare, all right? So that's why it makes sense, okay? Infinitely tall but infinitely rare, so it's okay. But it does mean that that distribution, like we might not have seen a 7-foot-tall student, but you can move along the x-axis to where the 7-foot-tall student is, and you can work out how much of the distribution there is for that 7-foot-tall or greater than 7-foot student. And if you didn't know, these statistics are used widely in finance and insurance, and there's money that's made on the back of these and making these kind of predictions. And you know, you'd have a better chance of having a bet with somebody about the likelihood of a 7-foot tall student. If you bothered to measure 500 students, you might not find a 7-foot tall student, but you could have a bet with someone. You'd know what the odds should be. They wouldn't. You've got a better chance of winning the bet because you know the odds. So maybe that would encourage you to do the exercise, because you might be able to have a bet with someone and win. Okay, look, we'll leave it there, because I'm with you tomorrow. Tomorrow we're going to talk some more about models and a bit more about statistics. Next week, I'm going to be doing a lot more to introduce the stuff we'll be doing on the field trip. And Neil's also going to talk to you next week. So, well, I'll see you tomorrow. If you get the chance, try and have a look through the material that you haven't looked through before. So, particularly this spreadsheet. That's probably the main thing. There's 2 tabs on this spreadsheet. And the error propagation. Like, really, error propagation, you definitely need to get on top of. If you've looked at those, if you've got any questions about them, then we can just cover that tomorrow. We can try and just go over that. Right. And if you haven't looked at the projects, so try and look at them. Given, tell you what, like for looking at the project, because that might take a bit longer. If you haven't done it, don't do that now. Do this work now. So for tomorrow, we've all looked at the spreadsheet, and we'll go over the projects, what people thought of them, not tomorrow, but next week. So there's a bit more time on that. Okay. I've recorded this session, so I'll put this on Blackboard. Okay. I'll probably also put the recording from last year on there as well, and you can choose which one to listen to. All right then. So I'll see you guys tomorrow. Actually, sorry, one last thing, just to be sure about something. Right, you should all, apart from the students that I'm contacting, nearly all of you should have been contacted by an academic advisor. Have you got emails from an academic advisor asking you to come along to a meeting with them? Will you do me a favour? You put your hand up if you have. Yeah, put your hand all the way up. I just want to see, because I need to show people that. There's quite a lot of you. Right, if you haven't, don't worry. Very soon, like probably in the next week, you'll get an email from somebody. The role of the academic advisor is just, they'll meet with you maybe once a semester, just to ask you how things are going, whether things are okay. So it'll just be one-to-one with an academic advisor. Only once a semester. They'll just check with you. They'll let you know who they are, and if you have particular problems, you can speak to them as well. So expect to get an email, and expect to have a meeting with them once in the semester. So once this semester, once next semester. This is different to your tutorial tutors. And for most of you, the tutorial tutors, you won't be in contact until next semester, apart from the meeting students. So you should be contacted by a tutorial person and an academic advisor. Okay. All right, I'll see you guys tomorrow.